Welcome to lecture 3.2. In this lecture, I'll be predicting the aromaticity or anti-aromaticity of fully conjugated rings by introducing this rule made by a man named Huckel. That's Huckel's rule. So, looking at this number line here quickly, I want to point out that non-aromatic rings can be viewed to be in the center of it. The idea being that this non-aromatic ring doesn't really enter the idea of aromatic theory. It is still a conjugated system, don't get me wrong. It's stabilized by that conjugated system, but we don't view it through the lens of aromaticity unless it's a fully conjugated ring. However, that's not the whole story, as the molecule on the left and right here are both fully conjugated rings, but as mentioned previously, are very different in terms of their stability. Something about benzene makes it incredibly stable. It's aromatic. This is where the aromatic rings will go. And there are many more aromatic rings other than benzene that we'll introduce. However, cyclobutadiene that seems to fit that first rule, right? It's a fully conjugated ring. It's incredibly unstable, and we call this anti-aromatic. So how can you understand this rule? Well, we need to look to Huckel. Huckel's rule states that the stability of a fully conjugated ring depends on the number of electrons in its pi system. Luckily, we just finished the conjugated systems topic, which means that we know how to calculate that. So the idea is that if the number of electrons in that system is equal to 4n plus 2, your ring will be aromatic. But what does 4n plus 2 mean? Right? 4n plus 2 is going to be assuming that n can be any whole number. It can be 0, it can be 1, it can be 2, it can be 3, and so on and so forth. We'll just look at those four numbers. Let's plug in 0 as n, 1 as n, and 2 as n, and see what happens. So 4 times n, 4 times n, and 4 times n plus 2. When we use these equations, right, 0 plus 2 is 2, 4 plus 2 is 6, and 8 plus 2 is 10. Once again, this is as hard as math gets in organic chemistry, something that I'm eternally thankful for. It's hard enough as it is. The last thing we need is complicated math. So if your system has 2 electrons, 6 electrons, or 10 electrons, it will be incredibly stable. Looking at benzene, we can see that in terms of its pi system, it has 2 electrons, 4 electrons, and 6 electrons total. That fits the 4n plus 2 rule when n is equal to 1. The idea is that only one of these equations will fit at a time. So when you have your number of electrons equal to 4n plus 2, your ring is stabilized by aromaticity. But what happens if you have 4n electrons? Well, we can do this math again. 0, 1, and 2. 4n without the 2 is going to give us 0 electrons, which obviously is kind of nonsense. 4 electrons, 8 electrons. Notice that there's no overlap. Any number that this equation gives you will never match a number that this one gives you. And the idea is that if your fully conjugated flat ring has 4 electrons or 8 electrons or 12 electrons, right? Whatever it is, it equals 4n. That means that your ring is going to be destabilized, and we can call that by anti-aromaticity. We'll dig into the real mechanism of this in the next video. For now, let's finish up that complete flowchart that I introduced last video. You identified a cyclic conjugated system, and you first asked, is it a fully conjugated ring? Right? It also needs to be fully flat. If the answer is no, then your ring is simply non-aromatic and you're done there. A common mistake students are going to make is they're going to start counting the electrons in a non-aromatic ring, and they're going to apply it to Huckel's rule. For example, here we say that there are 4 electrons in the pi system, but that does not mean that it's anti-aromatic. It is non-aromatic because we didn't even pass the first step. Then, if it is fully conjugated, we apply Huckel's rule. We count the number of electrons in the pi system, and based on that determination, we can determine if the ring is aromatic or stable. That's if it fits the 4n plus 2 rule, or anti-aromatic. Let's do a couple examples to really figure that out. Starting with the molecule on the left, I see a ring, I see some conjugation. Let's identify if that ring is fully conjugated. Feel free to pause the video and take a stab at these problems. But I'll get started. I see a conjugated diene, and hey, there's a carbonyl here. Right? These are all sp2 hybridized orbitals that have conjugation, right? These p orbitals, or sp2 atoms that have p orbitals, I should be clear. But notice, once again, we don't have a fully conjugated ring. So this is simply non-aromatic. Right? I can view this from a conjugated systems perspective, but not aromaticity. Looking at this ring, right, I notice 4 different pi bonds. We have a diene there that looks conjugated. A carbocation, remember, doesn't provide any electrons, but it does provide an empty p orbital, which can be used, and we have a fully conjugated ring. Remember that carbocations are sp2, they're flat, which means that we have a flat conjugated ring, and now we have to count the number of electrons in its system. Right? To do that, we count the number of pi bonds and lone pairs that are involved. I count 2 pi bonds. Remember that the carbocation does not provide electrons. That is 4 electrons. Remember that if it's 4n plus 2, we're aromatic, and we're anti-aromatic if it's 4n. 4 electrons does not fit this rule, but it fits 4n when n is equal to 1, meaning that this ring is anti-aromatic. Now that's actually something that's really interesting. I want to take a moment to talk about that, because this is a big deviation from what we previously understood given resonance. If I showed you a carbocation, this one versus this one, up until this moment, you would have probably said that this molecule is more stable. It can better hold the positive charge. After all, you can draw resonance forms with it. Right? If I try to draw resonance forms, it looks like we have good resonance forms here. Aromaticity is a new little thorn in your side you have to watch out for when you're dealing with these ring systems. Right? It's actually way less stable than your typical carbocation. Anti-aromaticity is a massive problem. So this ring is surprisingly unstable. Now let's do this last ring. Looks quite interesting, right? But at the end of the day, we see 3 sp2 orbitals. It's a flat ring. It has the potential to be aromatic or anti-aromatic. We count the number of electrons, and I only see 2. That's going to fit the 4n plus 2 rule when n is equal to 0. It's never going to fit the 4n rule. That means that this ring is actually aromatic. So not only would we predict it to be stable because of resonance, but it's actually more stable than we would even expect like that because of the aromaticity. Right? Things like this can actually be a factor in reactions to come. If an intermediate is made that looks really unstable, you might think that it's a bad reaction. But if it generates an aromatic intermediate, maybe it's not so bad. That's why it's important to be able to understand how aromaticity can play a factor. But before we go any further, let's go to the molecular orbital theory explanation to understand why anti-aromaticity is so bad. Because again, that's kind of antithetical to what we saw previously using valence bond theory. I'll see you in the next video to discuss the Frost diagram.